Hi everyone. Okay, so I'm going to give you these little video lectures. So right now I'm going to just cover the end of what we didn't cover in the notes from, oh man, when was it? Wednesday, I believe. And, and then I'll start into the new lecture, which is going to be on PCA. Okay, so let me just remind you, we were talking about nonparametric methods. Nonparametric methods are a family of methods that we use to estimate the density of some unknown distribution that you're getting samples from. And so we've talked a little bit about estimating those densities when we think it's coming from some type of parametrized distribution, like a Gaussian distribution or an exponential distribution. And then you're just going to estimate the parameters that describe the distribution, and that's all you have to do. If you don't have any idea what kind of distribution you're working with, the data is coming from, you might use one of these non-parametric methods. And the simplest kind I showed you was this idea of the histogram method. So I want to kind of go back and really briefly mention the difference between the histogram method and the kernel density estimator that I then presented right after. Okay, so just to remind you, we talked about the histogram method where we divide up our space into these blocks, and then we just actually count the number of occurrences inside of the block, and we estimate the density based upon how many of those land inside of the blocks. Okay, and then we moved over and we said, okay, now if we want to use this idea but in a slightly different way to predict the density using a kernel density estimator, what we're going to do is estimate the point-wise density, right, P of x, as this function and this k was initially we saw it as a counting function, so it was just counting up the number of points inside of a box around x, and we would be kind of computing then almost something like a histogram there. We'd be just counting how many occurrences happened in the correct cube, really hypercube. Now one thing I want to highlight is these are the same idea but slightly different. So in this type of a method, you fix your discretization of the space. So here you might, initially form your grid of space, and then as things come in, you just let them land where they will and count them up, right? And so if you think about it, the estimation of the density for any points in this box will be the same. It's just given by the fact that there are 3 points that have already landed there, right? So if you're estimating either this target density value or this target density value, they would be the same. Now the situation is different over here. We don't fix the discretization or the gridding of space first. Over here, instead, what we're going to do is we're going to pick a target point, right? And then we construct a cube, a hypercube around that point. And then we look back and we say, okay, how many data points had fallen? Of the ones that we've already received, how many of the data points have fallen inside of this cube around x? So if you imagine for a slightly different target value, right, it will have a different box and a different number of data points that have landed in it. So that we no longer have this necessarily constant on cubes structure that we had over here. We're still going to have what we talked about before that was less than ideal, these discontinuities, steps in the density, because if you imagine jiggling this box around a little bit, you don't lose any of the points in that box, right? So if you move it like this a little bit, it's still the same density value. Okay, but we no longer have this initial gridding of space happening before we do anything. Okay, and remember we said, okay, this specific one where we used the counting kernel was less than ideal because there were these discontinuities, but we could generalize it by using a Gaussian kernel function. And in general, you can use any kernel function. So let me just briefly say, I want you to recall what we said before was that a kernel function measures some sort of a similarity. It's almost like a distance. Okay? So in general, we can use this type of an approach. And we have to use the proper normalization, and you would figure that out based on the kernel you chose. So we can choose any kernel and a kernel function is just a function that is always non-negative and integrates over all of space to be 1. Okay, now, so these are kind of the same types of ideas. We think about the type of kind of region we want to deal with, right? And so here we said we wanted to deal with cubes, and we just stuck cubes, non-overlapping cubes everywhere. Here we said we want to deal with cubes, and we stuck a cube around the point of interest, whose density we were trying to estimate. There's a different thing that you can do, slightly kind of reverses the idea called nearest neighbor methods. Okay, so instead of fixing the region or the volume of the region and counting the number of observations in that region, what you'd instead do is fix a number of points you're going to try to count, so fix k, and then you're going to inflate or expand a region until you've counted k points in the region that you've expanded. So imagine, you want to know what's the density sitting at this point, and what you're going to do is stand at that point, decide what your number k is. Maybe you say, I want my 3 nearest neighbors, and you inflate the ball around you until 3 of your neighbors are sitting inside of that ball. And once you've gotten that, once you've inflated the ball, the density is going to depend upon the volume of the ball that you've inflated. Okay, I won't give the specific details on this type of a method, but you can use this type of an approach not only for density estimation, but also for classification. We'll see lots of other approaches for classification in the future. Okay.